Suppose at the demodulator side, we do not have, we do not have a signal which is available at the carrier frequency, because as we saw in the Armstrong's diagram, there were many frequency translations. Sometimes the carrier frequency was translated, sometimes the frequency deviation was changed. So let's have a look at another code, which is the same thing that we have done here, but with some modifications. For a general signal, this code has been written. So this is the case where we have done FM demodulation for FM wave with constant amplitude. Mind here, the term constant amplitude is used because we are not doing any amplitude modulation here, and the signal that is received, it is free from noise. So the amplitude has not been tempered in any way due to the channel. And we will address the issue of this amplitude change because of noise a little later, but let us first understand this without this amplitude change and different signals and with or without frequency mixing. So this code will serve multiple purposes. So let's have a look. This is the same code that we have just seen, with the change that instead of using only one modulated signal here, we have two modulated signals. One is the message signal 1, which was the case that we have shown just now. And I have also created this message signal 2, which is a square wave to begin, a square or a rectangular kind of wave to begin with. So you could use either message signal 1 or message signal 2 for modulation purposes. So in this case, we can use any of the signals by assigning message signal a value of message signal 1 or message signal 2. So in this line number 28, you can do that. So we will see it with both of the results. And the another change that we have used here is that we are also using this frequency mixer or frequency converter. Remember, the frequency mixer or frequency converter is a device which will shift the frequency or the carrier frequency of the signal from some frequency to a desired frequency by using this f mix, right? So this code can be used either by using these lines, or you can comment these lines and the code will run still the same, because when you talk about this envelope detection, this envelope detection is essentially, going to detect the envelope of signal, irrespective of whatever frequency it is present at. So these two operations have been applied here, right? So let us see the output first for the case of message signal 1, which was a signal which we have just seen. So let me run this code, and let's see the output here. Here an additional thing is added, which I will explain to you in a while. So here you have got three plots. So let's see the first plot. It's a simple frequency modulated signal. I'm not zooming it again. If you see the demodulated signal, now here the amplitude variation which I was talking about is visible here. I haven't compensated it for amplitude. I haven't multiplied it by a number such that it becomes equal to the signal which was message signal. So that is perfectly acceptable. The only point is your frequency should match. Now the next thing is, I was talking about the frequency of low pass filter which we need to use. So here we have got this frequency, and now frequency of low pass filter has been taken as 10 into FM here. So this is also plotted in this diagram. So now here the blue signal is the message signal, and around that you have constructed this filter. Earlier we have taken only 1.5 of the FM, but here we have taken it 10 times. So let us see what happens when we take it to be 1.5 times of FM. So 1.5 times of FM, I think it will be okay, because again your blue signal is perfectly covered in that. So that is the case here. If you see it here, your blue signal is, if you zoom it, your blue signal is completely covered in your green signal. So it's well within the boundaries of this blue signal. So that's why the output that you see here is again a perfect output. The frequencies match, right? So that is why this additional step has been done here, and you can change this frequency of low pass filter by just observing the graph in frequency domain. This usually happens when we demodulate a frequency modulated signal. At least we can see the spectrum for the received signal, and from there we can just apply a filter of appropriate size. Now let's talk about the second signal that we have. Instead of using the first signal, let me use message signal 2 here. So this message signal 2, if I run my code, now you will see it's a square wave to begin with. So I will only show you the graph number 2 and 3. So this is my graph number 2, where this blue signal is your message signal, And the demodulated signal that you see has got the same frequency, but it is not a square wave. Why is it not a square wave? Let us see the third graph first. Now in the third graph, if you will see this plot of this message signal, it is way much larger. Blue signal is way much larger as compared to green signal. So there has been an abrupt truncation of this Fourier transformation terms. So we need to broaden this filter to make that sine signal that we are having in this output, in red output, look like a square wave. So let me just change the low pass filters cutoff in these lines. Instead of taking it as 1.5, let me take it as, say, 10 again. So if I take 10 and then see the output, so on taking the frequency as 10, for the low pass filter, you see that most of the signal is now covered, right? A better approximation could be you could take it 20 or 30, so most of the signal will be covered then also. But then again, let's see how the output looks like. So here you see now the signal has started to look like a square signal. If I zoom some portion, you can see that with a little Gibbs phenomena present, uh, the fringing is there, but then again your signal starts to look like a square wave. This you might have seen when you have done your Fourier series experiment. If you take truncated Fourier series, then your square wave will not be there, an approximation to square wave will be there with some Gibbs phenomena here, right? So that Gibbs phenomena is available here also. And if you take, your carrier frequency, if you take your cutoff frequency for low pass filter, say 20 times, then you might get a better result. So let's see that also. So in this case, yes, now the cutoff frequency is 20 times. So let's see the result again. Yeah, so you are getting a square wave, a closer approximation to a square wave. So if you will take it more, then your square wave will be better. So my point of telling this was that this code in general can be used for any frequency modulated signals demodulation. You could use signal number one, signal number two, or any signal of your choice. You can just design that signal here and use it. And another point to note is that when we have this frequency modulated signal here in this particular section, so we are assuming that no noise has been added to it and the signal is not distorted in any way. However, if the signal is distorted, so on reception onto the receiver, this frequency modulated signal will not be a perfect sine wave. It will be a distorted sine wave. So to remove the distortion, we have something which is called as band pass limiter. What we do is we first of all make the amplitude of the received corrupted sinusoidal uniform. That means initially if the sine wave had an amplitude between +1 to -1, then after corruption it becomes between say 1.5 to -1.5. So we will clip off that signal between +1 and -1, and then we will pass it through a band pass filter which is centered at the carrier frequency of the signal. So your sine wave will become perfect sine wave again, which you were receiving in this FM signal. So that band pass limiter can be applied, and in that way the same procedure can be used for demodulation purposes. So in this video we have learned a lot of things. We have first learned the fundamentals of how to demodulate a frequency modulated signal, and we have seen some practical aspects also of how demodulation is done. One more important point is, which is important for coding purposes, the length of the signal that you use here. For example, while generating your this sampling theorem, this length of the signal that I am using here is 50,000. In earlier codes it was 5,000. So if you change it 5,000 or 500, so if you change it to 500 again and then you see the results, your final results will not overlap exactly, right? So let me see it here. Your final results will not overlap. Why? Because to be able to do experiments on sinusoidal signal, we need to have a lot of samples. Because ultimately, even if we have a very large number of samples, the signal cannot be made sinusoidal, because ideally sinusoidal signal is infinite in extent. So that is why instead of using low number of samples here, you need to keep the samples high so as to be so as the results that you have are perfectly replicated. Otherwise you will believe that you are doing everything correct and not getting the correct result. So this point should be kept in mind. So this is for from the perspective of coding itself. So this is an important point, right? So in this video we have learned a lot of things regarding this theory of demodulation and how to code this signal, and we will talk about other ways of this demodulation of FM signal in the coming videos. And this complete theory is applicable to the demodulation of angle modulated waves in general. All you were interested in is either instantaneous frequency, and from instantaneous frequency, the phase can also be calculated. We already know this. And if phase and instantaneous frequency are available, both phase and frequency modulated signals can be demodulated. So this procedure is general and can be applied to any kind of angle wave. Or alternatively, you can also use a frequency modulated wave as phase modulated wave by applying differentiator or integrator, which we have already discussed. So this is it for today's video. Thank you very much.